Great, let's get started. So Geoff Pleiss is a postdoctoral researcher at Columbia, hosted by John Cunningham, with affiliations in statistics and the Zuckerman Institute, which is sort of a mind, brain, and behavior institute. He obtained his PhD in computer science from Cornell with Kilian Weinberger, who's well known in machine learning, and his bachelor's at Olin College for Engineering. His research interests are broadly situated in machine learning, including neural networks, Gaussian processes, uncertainty quantification, and scalability. And he co-founded this Gaussian process GPyTorch software framework and maintains that community online. Take it away, Geoff.
All right, thanks, Blair. So today I want to talk about my work in two machine learning paradigms, in deep learning and in probabilistic modeling. And in particular, I want to discuss how I aim to combine the strengths of these two worlds using insights from one to improve the other. And before I dive into the details of that, to motivate why we want to look at these two paradigms in particular, I want to paint a picture of two very different settings where machine learning has been successful today. And in the first setting, our goal is to extract semantically meaningful information from complex data. So we might have, for example, a set of natural images, and our goal is to be able to detect objects in those images. Or we might have a large set of text documents, and we want to classify those text documents based off of their content. Now, models that excel at these types of tasks fall into what I call the high power regime. And this is going to be characterized by models that are accurate, especially on these complex data modalities, but also models that are going to be scalable, so that can make use of the wealth of data that we now have available to us. And the models today that best exemplify this high power regime are neural networks. They're going to be best suited for these types of predictive tasks. So now let me paint you a picture of a totally different setting where machine learning has been successful. And here in this setting, our goal is to develop models that aid in downstream decision-making tasks. So for example, let's say that we want to predict future health outcomes for a newly born infant. We might use a machine learning model to forecast what this child's weight might be in the future based off of early health records. And our model may report that there is a sufficient risk that this child is likely to be underweight in the future. Now, being able to reliably quantify this risk and reason about it is going to aid a medical practitioner in making an informed downstream decision to potentially prevent this potentially bad health outcome. So models that excel in these settings where we need to assess risk and reason about downstream decisions fall into what I call this high reasoning regime. And this is going to be characterized by models that are aware of uncertainty in the real world and are able to incorporate that uncertainty into the predictions. They also generally tend to be domain specific, so able to incorporate prior knowledge or expert knowledge that we have about the world. And they're also generally intuitive, so built from understandable building blocks. And today, what best exemplifies this high reasoning regime is going to be the framework of probabilistic modeling, which for the purposes of this talk is the paradigm where we're going to be inferring a distribution over statistical models conditioned on some set of observed data. And I'll dive into a little bit more what I mean by that later on in the talk. But those are two very different settings that I've described where machine learning is successful today. And if we look to the future, we're going to need models that live in both this high power and high reasoning regime. So let's think about what we want machine learning models to be a part of in the future. Settings like driving autonomous vehicles or guiding policy decision or informing scientific discovery. And in these settings, we will undoubtedly come across complex and large scale data. So we're going to need models that are going to be accurate, especially on these complex data modalities, and also scalable. But at the same time, these are high stakes decisions, and incorrect downstream decisions pose substantial risk. And so we must be able to properly assess and mitigate that risk. So we're going to need models that can quantify uncertainty, incorporate expert knowledge, and generally behave intuitively. So in short, we really need the strengths of both of these two paradigms. And if we think about where we are today, we need significant developments to get to this high power, high reasoning regime. So today's current set of models often constitute a trade-off, where we can either get one or the other. Neural networks, for example, tend to fall into this high power but low reasoning regime. Again, they're very accurate, especially on complex data, but they're also prone to being miscalibrated, unconstrained in their predictions, and generally black box and hard to intuit. And to briefly demonstrate this, let me show you that the accuracy of a neural network often comes at the cost of a miscalibrated notion of uncertainty. So imagine we had a pedestrian detection neural network, say as part of a self-driving car. Now we'll feed images into this neural network, and this neural network is going to output a score for each image that can generally be interpreted as the probability that there is likely a pedestrian in that image. Let's group these images based off of the score that our model assigns. And let's, for example, consider the set of all images where our model makes a prediction and assigns a score of 70% confidence. Now, it should actually be the case that in 70% of these images, there should actually be a pedestrian. This is the definition of a well-calibrated uncertainty estimate, which basically means that our neural network is accurately modeling the ground truth likelihood that we observe in the data. And it should be straightforward why this would be a desirable property for a predictive model. It means that we can trust the uncertainty estimates that it produces. So I trained a common neural network, a 110-layer residual network, on the standard CFAR10 image classification dataset. And what I'm showing you here is a subset of images from the test dataset where the model made a prediction and assigned that prediction a confidence score between 80 to 85%. Now, based off of this definition of calibration that we just talked about, it should be the case that 80 to 85% of these predictions are actually correct. But that's not the case. In fact, this neural network actually got over half of these predictions wrong. So that 80 to 85% confidence score that's being output by the neural network is wildly overconfident. And it shows that we can't trust the uncertainties that are output from this model. But it gets even worse. What I'm showing here now is a plot of the accuracy of this model and its miscalibration as we add more layers to this neural network. So additional depth is going to be beneficial for the accuracy of this model, which we can see from the blue line here. We see that error decreases when we add more layers. But also, adding more layers makes this model more miscalibrated, as we see from the red line. So this accuracy that we celebrate in neural networks, which to a large extent has come from making these models deeper, also comes at the cost of unreliable uncertainty estimates.
Sorry.
Yeah.
How were those confidence estimates calculated? Are you going to get into that?
I probably won't get into it in this talk here. The confidence estimates in this case, since it's multi-class classification, it's just going to be the output of the softmax layer in a neural network, and just thinking about the most likely class according to that softmax. So this example here just focuses on a few of the dimensions that we care about, but it illustrates that these reasoning capabilities of neural networks leave something to be desired. And later on in this talk, we'll see that current probabilistic models are going to fall on the opposite end of the spectrum, this high reasoning but low power regime. They're not going to be as adept at handling these complex data types, and they're also not going to be able to scale to some of these large data sets. So the goal of my research is to expand this Pareto frontier. I aim to develop models that are capable of both high power and high reasoning. And we don't need to go back to the drawing board to do this. What I show in my research is that it's possible to increase the reasoning capabilities of neural networks without sacrificing their power, and also possible to improve the power of probabilistic models without sacrificing their statistical grounding or reasoning capabilities. So for example, while I do demonstrate that neural networks are prone to being miscalibrated, I also showed that it's possible to alleviate this miscalibration with simple post-processing techniques, such as scaling the untransformed outputs of a neural network. I won't go into too much details about this approach now. I'm happy to chat about it more offline. But crucially, this post-processing approach does not affect the accuracy. The blue line remains unchanged, which means that we can use these deep and accurate models, and in many cases have near perfect calibration. There's lots of limitations to this approach, which I'll come back to at the very end of my talk, especially when it comes to so-called out-of-distribution data. But it's a first step towards getting neural networks that are also capable of modeling uncertainties. And so beyond miscalibration, my work has focused on pushing this Pareto frontier in multiple dimensions, with one line of work focusing on improving the reasoning capabilities of neural networks, and another line of work focusing on improving the power of probabilistic models. And today I want to tell two specific stories from these lines of work. And beyond just describing the improvements that I make in these papers, what I hope to convey through these two stories is a central tenet of my research, which is while we can push this Pareto frontier if we work on neural networks or probabilistic models in isolation, the way we get to this high power, high reasoning regime is by applying insights from neural networks to improve the power of probabilistic models, and also vice versa, applying insights from probabilistic models to improve the reasoning capabilities of neural networks. So in the first part of the talk, I'll discuss a line of work focusing on improving the scalability of one class of probabilistic models, in particular, Gaussian process regression. And this line of work, as I hinted at, will draw heavy inspiration from my research in deep learning. And the second part of the talk will focus on the reverse story. I'll be describing some recent work towards better understanding neural networks and making them less black box. And again, this is going to be using techniques from my research in probabilistic modeling. So let's dive into this first part here, where again, we're going to be talking about Gaussian process regression. And let's return back to this motivating example that I described in the beginning of the talk, where we're predicting infant health outcomes, where again, we want to extrapolate the weight trajectory of a child into the future. Now, this paradigm of probabilistic modeling is considering a distribution of all possible models conditioned on a set of observed data and according to some prior. And by reasoning about a distribution of possible models, the result is rather than getting a point prediction, we instead get a distribution of all plausible outcomes. And this is very beneficial because with this distribution of outcomes, we can then better assess risk and reason about potential medical interventions. Gaussian processes are a specific type of probabilistic model where importantly, this distribution of outcomes can be computed in closed form. There are analytic equations for this average prediction in the middle, as well as this uncertainty estimate. And I won't get into the analytical equations now, but this is really what sets it apart from a lot of other probabilistic models, where getting these uncertainty estimates would often require sampling or approximations. And here's a Gaussian process model that I developed in collaboration with the Bill and Melinda Gates Foundation, specifically for this task of predicting infant health outcomes. And when we apply this model to newly born infants, like we see over on the left, we extrapolate with high uncertainty, which is exactly what we would want because we don't have a lot of observed data. We should be uncertain about our predictions. As the infant grows older and we collect more data, we can start extrapolating with more uncertainty like we see over on the right, which is again exactly what we would want after we've collected more data. So these Gaussian processes are giving us a very rich notion of uncertainty, which again can be computed analytically. And this is what makes them really powerful, especially in these applications where we want to be reasoning about risk.
So when you say analytic,
yes.
So you have a closed form formulation.
Yes.
Is it easy to compute that? Because most of the
yes and no.
Monte Carlo and then
yes, so it's easy to compute in the sense that it is a straightforward equation that doesn't require any sort of sampling or any sort of approximations. Like I can write down the equation and you can compute it in a few lines of like MATLAB or Python code. But the big catch, which I'm just about to get to, is that even though there are these analytic equations, they can be computationally expensive. So imagine that we want to apply a Gaussian process to a data set with 1 million data points. As a back of the envelope calculation, this is going to require about 600 quadrillion floating point operations, which is roughly the cost of inverting a 1 million by 1 million matrix. And based off of these numbers, you might think it's wholly impractical to try to use these Gaussian process models on such large data sets. Until that is, you consider the cost of neural networks. So this dense net with 264 layers used to be state of the art for many computer vision tasks. And training this model on the 1 million data point ImageNet benchmark dataset requires 2 quintillion floating point operations. So a whole order of magnitude more. And yet the community has shown that it's actually possible to train these models in as little as 3 hours or as little as $25 of AWS compute. So how is it possible that this one model, which is actually more computationally expensive, is somehow considered practical? The answer is it's not the number of floating point operations, but the type. And in particular, Gaussian processes are going to use what I consider to be smarter numerical operations, by which I mean numerical operations that are going to be more amenable to distributed and parallel hardware like GPU compute clusters that are now so commonplace. And so let's take a lesson from neural networks here. The computations for large-scale Gaussian processes might be practical if we can make Gaussian processes more numerically similar to neural networks using the same computational primitives that are better able to exploit GPUs and distributed hardware. So how do we do this? At a high level, this is basically what we need to do if we want to use a Gaussian process model in practice. We start off with some training data set with n data points, and then we're going to compute an n by n covariance matrix, where each entry of that matrix corresponds to essentially the pairwise similarity between any pair of data points. With this matrix, we need to compute two terms, a matrix solve, K inverse Y, and a log determinant of that covariance matrix. And with those two terms, we then have basically everything we need to now perform inferences with our Gaussian process model. The computational bottleneck comes from computing these two terms here. And the way this is typically done is through the Cholesky factorization of our covariance matrix, where we're essentially decomposing this covariance matrix into a lower and upper triangular matrix that are transposes of one another. Once we have performed this decomposition, it's relatively easy to compute this matrix solve and the log determinant. But computing this decomposition in the first place this is really where our computational bottleneck is. It's going to require a cubic amount of computation in the number of data points we have, and also a quadratic amount of memory. And though it's possible to do this Cholesky factorization on GPUs or distributed hardware, we're not really going to see the gains that we need to really apply these models on large data sets. We're not going to get quite the level of acceleration that we need from GPUs. And if we want to distribute this computation over multiple devices, it's going to require a lot of communication between those different devices. And so we're not going to eke out all the parallelism that we would need for these very large scale models. So to solve this, what I propose doing is replacing this Cholesky factorization instead with an algorithm that's entirely built on matrix multiplication. And why matrix multiplication? Well, it's the highly parallel computational primitive that basically underlies most of neural networks. And in fact, GPUs, which are so commonplace nowadays for most of our machine learning compute, were explicitly designed to accelerate matrix multiplication, making it so that it can be 10,000 or even 100,000 times faster than when we do it on a CPU. And along the way, what we'll see is it's not just going to be a practical speed up, but we can also get asymptotic improvements as well. With this matrix multiplication approach, I can compute this matrix solve and log determinant up to 4 or 5 decimal places of accuracy, or more if desired, in a quadratic amount of time and a linear amount of space.
But you're assuming that the covariance matrix has some sparsity.
No sparsity. It is going to be positive definite, and it can be computed from data which can be stored in a linear amount of space, but no sparsity assumptions.
You need to store them like the matrix offline or you on the fly.
Right. So that I'll kind of like touch on this later, but that's sort of how we're going to be able to reduce this down to. Sorry, I have to burn things again. This is how we're going to get this linear complexity is essentially by not having to store this matrix, but instead being able to compute one row at a time from our data, and then performing a matrix multiplication with that one row. And I'll touch more on that later, but that's how we're able to get the linear complexity, or linear memory complexity, that is. So how do we go about doing this, reducing these two terms down to an algorithm that relies only on matrix multiplication? For those of you with a background in numerical methods or optimization, you're probably familiar with the method of conjugate gradients, which is an iterative algorithm for computing matrix solves using only matrix vector products. And for those of you who are not familiar with it, this is at a high level how it works. We're going to start off with an initial guess to what our matrix solve is, C naught. And then we're going to reframe this matrix solve as an optimization problem, where we perform several iterations to refine this guess. And each iteration is specially designed in a way that only requires a single matrix vector product. After n iterations, we're guaranteed an exact arithmetic to arrive at our true matrix solve, K inverse Y. But in practice, we often need way fewer than n iterations to arrive at several decimal places of accuracy. This algorithm converges very, very quickly. And just to put a concrete number into the mix here, the exact number of iterations that we need depends on a lot of factors, like our data, our choice of covariance function. But in a lot of Gaussian process applications, I've seen that with, say, 15,000 data points, we can often get away with as few as 200 matrix multiplies in order to achieve, say, 4 or 5 decimal places of accuracy, which is often going to be good enough for what we care about. Now, conjugate gradients has been used before in conjunction with Gaussian process inference. It's a very historic algorithm, but typically it's been relegated to special cases where there's explicit structure that we can exploit in the covariance matrix. And here the goal is to convert conjugate gradients into this general workhorse algorithm where we can not only get this matrix solved, but all the other terms that we need for Gaussian process inference in the general case, and really, again, designing it to explicitly exploit GPU acceleration. And to do this, we're going to need to make a few modifications. So what I show in my research is that with a little additional bookkeeping, we can also get unbiased estimates of this log determinant term here, essentially for free from the byproducts of this conjugate gradients algorithm, with very little additional math. And in addition, I introduced a low rank preconditioner specifically designed for Gaussian process covariance matrices. What this preconditioner does is it's going to accelerate the convergence of this conjugate gradients algorithm, meaning that we can often achieve these 4 or 5 decimal places of accuracy we need in maybe a order of magnitude fewer matrix vector products. So now maybe as few as 20. And finally, in the case where 4 or 5 decimal places of accuracy may not be enough, I prove that the residual error of this conjugate gradients algorithm is guaranteed to be unbiased when we use it in conjunction with a simple randomized truncation scheme, which means that we can use this with any of our typical stochastic gradient optimizers and not be worried about any sort of bias creeping into the system, even if we're not computing these solves to completion. So this is the basis of what I call black box matrix times matrix inference for Gaussian processes, where again, we've taken this main computational bottleneck of Gaussian processes and reduced it down to about 20 matrix multiplies, each of which are going to be highly parallelizable and really able to exploit GPU acceleration. So to show you what this looks like in practice, I'm going to compare this black box matrix times matrix approach over on the left with the Cholesky approach on the right. I realize everything is really small on the screen. It's basically just going to be a quick training routine. There's not too much you need to see when it comes to the exact numbers here, but the big takeaway is that this black box matrix times matrix approach is going to be a lot faster. On this particular example here, it ends up being about 10 times faster.
Are you using GPU?
Yeah, for both, yeah. And so again, like the Cholesky factorization can make use of GPU acceleration, but the matrix multiplication approach is really going to be able to utilize it to a much greater extent.
Is Cholesky factorization does use any sort of parallelization or nothing?
There is definitely parallelization that it can exploit, but it's not quite as parallelizable as matrix multiplication. Where like with matrix multiplication, you can basically perform every single floating point operation you would need to completely in parallel, whereas there's going to be some inherent sequential nature to the Cholesky factorization. So I've mostly just talked about this algorithm in the terms of Gaussian process training or optimizing the hyperparameters of these models. But in a series of papers, I expand out this approach to really cover all aspects of Gaussian process inference, ranging from being able to make predictions with these models and also to be able to sample using sort of a very similar approach that only relies on matrix multiplication. So I've just demonstrated that it's faster, but can we do anything new with it? And I already hinted at this a little bit before, but the great thing about matrix multiplication is it's super easy to distribute across multiple devices. So if we have multiple GPUs available to us, we can break up this matrix multiplication into multiple subproblems, where each subproblem is multiplying a few rows of the covariance matrix by the vector we care about. We can assign each of these subproblems to its own GPU. And again, each of these subproblems can be performed completely independently, producing a few rows of the resultant matrix vector product, or sorry, a few entries of the matrix vector product that we care about. And afterwards, we just concatenate those together. This is really going to be highly parallel with very, very little overhead. And what this means is when we have access to large-scale computational resources, we can trivially exploit them for very large-scale Gaussian process computations. Which means now that it's possible to apply Gaussian process inference to datasets with over 1 million data points. Putting this into perspective, using standard approaches that relied on this Cholesky factorization, the previous limit that I had seen in the literature was about 20,000 data points. After this point, it's going to start running out of memory on standard compute devices. And again, even though it's possible to distribute this across multiple computers so that we can potentially use memory if we have a big cluster, there's going to be a lot of communication overhead. So this isn't really a practical approach to scale it up. In contrast with this matrix multiplication approach, we can train a Gaussian process on 1 million data points across 8 GPUs in about 4 hours, which I will still admit is a lot of computation. But again, this is 2 orders of magnitude beyond what had previously been thought to be possible. And now once we've trained this model, when we want to make predictions with it, we can do so on a single GPU in less than a second. So we may not always have access to these large-scale computational resources, but when we do, we've unlocked a new class of powerful models. And this isn't just an academic curiosity. What I'm showing here is this large-scale Gaussian process approach with these blue bars here, compared to what people had previously been using to approximate Gaussian processes on large data sets with the orange bars. And I'm showing this for a number of regression benchmark data sets. This is plotting error, so lower is better. And what we see is that on many data sets, these large-scale Gaussian process models, again in blue, can significantly outperform these previous approximations that people had been using. So this is a very powerful model that we now have access to.
So what was the horizontal, the vertical axis?
Sorry, the vertical axis is test set error, measured by root mean squared error for regression data sets. Yeah. So to facilitate the adoption of these new large-scale methods, my collaborators and I built a new software library for Gaussian processes called GPyTorch. The name, as you maybe guess, it is a portmanteau of Gaussian processes and PyTorch, because we built this on top of the PyTorch framework and we weren't very creative with our naming. But our goal with this framework was to make large-scale Gaussian process models very accessible. And again, this is drawing inspiration from the success that neural networks have had. Clearly, there's been a lot of advances in optimization and architecture design, but arguably a very big component in the success of neural networks has been just how accessible they are and easy to use due to software frameworks, making them very modular and easy to rapidly prototype and deploy. This is what we wanted to do for these large-scale Gaussian process models, to make it very easy to rapidly prototype with them and to deploy them in practice. And today, I'm pleased to say that GPyTorch has become one of the de facto standard Gaussian process libraries, not only used by researchers in machine learning and other scientific disciplines, but also actively used by many companies like JP Morgan, Meta, Lyft, and Mars, actively deployed in many of their products. And so this kind of concludes the first part of the talk, and I'd be happy to pause here for questions. But just to briefly recap, we've taken Gaussian processes, which again are this probabilistic model where we can compute these predictive distributions in closed form. And we scaled it 2 orders of magnitude larger than what had previously been possible by making these models more numerically similar to neural networks. So I can pause here if there's any more questions.
Have you compared your method with some traditional kernel approximate method like random for features or nice method?
Yeah, that's a good question. So that's what I was showing over here on this slide here. So this is with SVGP, which is essentially a fancy version of the Nystrom approximation is one way to think about it. And this isn't to say that there aren't cases where SVGP it isn't a good model for many data sets, but there are often going to be a lot of cases where some of these traditional approximations are not going to be well suited for all types of applications. And we generally found that this large scale approach with matrix multiplication can often outperform these more traditional approximation methods.
So when you did the preconditioning, I don't know, from your figure, I thought you meant you did something like the Nystrom approximation to the affinity matrix.
Yeah.
What did you do that was
Right. No, that's actually a very good point. So we didn't necessarily use a Nystrom approximation. We used, in particular, was an incomplete Cholesky factorization, which has a lot of similarities to a Nystrom approximation. I think that it can to some degree be viewed as a specific case of that. One way of viewing this, which is which I outlined in a recent paper that's under submission, is that the precondition, one of the ways that we can view conjugate grains is starting off with a traditional approximation method, which is defined by our preconditioner, and then doing iterative refinement on that. So to some degree, it could be seen as, we're starting off with this orange bar up here, and then we're just, running some iterations to make it better. And yeah, so there's a very deep connection there.
So you can view this as an Appalachian study.
Yeah, exactly. Yeah. And it does seem to be the case that, more iterations, not always, but many times seems to be better. If there's no more questions, I'm going to now switch gears and move on to the second part of the talk. where now we're going to focus on neural networks. But again, Gaussian processes are going to pop up in this part of the talk as well, where I'm going to demonstrate how they can be used as a tool to help us better understand neural network architectures and make them less black box and more interpretable and intuitive. So one of the many benefits of statistical models or probabilistic models is they generally have what I call intuitive structure. And what I mean by this is when we make a change to the model, we generally have a pretty good idea of how this change will affect the downstream predictions. So for example, let's say that we have this Gaussian observation model, which we're using to make predictions. What would happen if I replace that with a student T observation model? We have a pretty good sense of what would happen here. More of our data is likely to be interpreted as noise, and so our predictions that our model makes will tend to be more conservative. And so being able to intuit how our model works this way when we make changes to it is really useful because it'll allow us to trust our predictions more, and it'll generally make it easier to encode assumptions about the world into our models. So neural networks are going to be a bit more black box. It's going to be harder to intuit how changes to the architecture is going to affect the downstream predictions. So for example, what would happen if I made this neural network really wide? What happens to the types of predictions that we would expect to see? And it turns out this is actually a pretty hard question to answer because the effects are going to be rather counterintuitive. Before I dive into that, I want to spend just a few brief moments talking about what is so special about neural networks. What is our intuition for why they are this really powerful class of models that can work well on these complex data sets? And to do that, we need to contrast neural networks with so-called shallow models, which is going to include things like splines and kernel methods or wavelets or things along that nature. And the way that shallow models work is we're going to take our input and we're going to use a set of basis functions to extract features that describe this input. We then take these features and we linearly combine them to form a prediction about this input. Now, crucially, these basis functions that we're using to extract features about our data are fixed a priori. And in this sense, the basis functions themselves are data independent. And sometimes our choice of basis function is not going to be well suited to the type of data that we have in practice. For example, if we use these 4 Gaussian bumps as basis functions, no linear combination of them is going to be well suited to make predictions on the step function data that we see over here on the right. And of course, this is a very trivial example. There's clearly a better set of basis functions we could use to extract better features for the step function data. But as we scale to problems that are more high dimensional, it's not going to always be clear what types of basis functions are going to be well suited for this particular task. Neural networks work a little bit differently. So they're also extracting features and forming a linear combination of these features to make predictions. But crucially, these features are going to come from basis functions that are learned directly from the data. In this sense, our basis functions are data dependent rather than being data independent. And the result is we'll have a set of features that is going to be much more well suited to the data at hand. We might end up, for example, with a set of notch functions over here in the middle, which are going to be perfectly aligned with the steps that we see over on the right. So with this intuition in place of neural networks performing a set of learning a set of features from data rather than having a fixed set of features, let's go back to this question now of how width affects neural network performance. And again, knowing this question is going to help make neural networks less black box. So prior research gives us insight into 2 phenomena that occur as neural networks become really wide. On one hand, more width means that we have more access to features that can describe our data. And this is generally desirable. With more features, we're going to be able to describe more complex functions. And in fact, we know that in the limit of infinite width, neural networks become universal approximators, meaning that a neural network has the capacity to model any continuous function to arbitrary precision. On the other hand, there's a more stranger phenomenon at play as well. It's also true that in this infinite width limit, neural networks lose the ability to learn features from data. And in particular, what this means is that when we train the neural network on a set of data, we end up with a set of basis functions that are exactly the same as if we had trained this neural network on a completely different set of data. So what this means is we have a fixed basis, meaning that these infinite width neural networks aren't any different from these shallow models that I was talking about earlier. So this is a classic result that neural networks lose the ability to learn features in the infinite width limit, but it's also one that's received a lot of renewed interest because it's a very strange and unsettling phenomenon. Again, remember that being able to learn features from data is supposed to be what makes neural networks so powerful in the first place. What makes this really confusing and hard to reason about is that width is conflating these two phenomena here. We go from having a finite set of features that describe our data to an infinite set of features. And this seems like a good thing. But again, those features go from being learned from data to then being fixed. And that doesn't seem like such a good thing. It's not immediately obvious which we would prefer, a finite set of learned features or an infinite set of fixed features. So to grapple with this, I propose running a control experiment that's going to be easier to reason about. We have these two variables here that change with width. Let's decouple them. I want to now compare the difference between a model with an infinite set of learned features and a model with an infinite set of fixed features. To do so, we're going to need to consider a neural network model with a slight modification, this so-called bottleneck neural network architecture here. And this is going to be a neural network where we alternate between having layers with an infinite amount of width and so-called bottleneck layers that have a finite amount of width. This is inspired by lots of models that we use in practice, such as autoencoders or generative adversarial networks. But these models haven't really seen a ton of theoretical analysis. It turns out, though, that they're going to be the perfect architecture for this control experiment that we want to run. I proved that these bottleneck neural networks do in fact correspond to an infinite set of learned features. It's an infinite set of features because this last layer down here is infinitely wide. But crucially, this bottleneck layer in the middle is going to prevent this model from collapsing to this limiting case where we just end up with a shallow model with fixed features. I don't want to go into too much detail about how to show that these bottleneck neural networks do in fact correspond to an infinite set of learned features. But at a high level, I'm just going to give the very high level proof technique because it's going to tie back to the main theme of the talk here. It turns out that bottleneck neural networks are a subclass of models known as deep Gaussian processes, which is what we get if we take multiple Gaussian process models and stack them together hierarchically. Lots can be said about these deep Gaussian process models, but for the purposes of our talk, this reduction now makes it possible to analyze bottleneck neural networks with the theory of Bayesian nonparametrics. And this is going to give us a tool to formally describe this idea of feature learning and show that it does in fact occur in these bottleneck models. So what we have now is we have a model with provably infinitely many learned features. What now happens is we increase the width of this bottleneck layer. Well, as this bottleneck layer grows wider and wider, it ends up being the same width as all of our other neural network layers. And we know what happens to an infinitely wide neural network. It loses the ability to learn features. And in particular, I show that the width of this bottleneck layer, to some extent, controls how much feature learning occurs. So the width of this bottleneck layer becomes a knob that we can turn to control how much feature learning we want to occur. And again, this can be formalized through the lens of Bayesian nonparametrics. So now what happens as we increase the width of this bottleneck layer and lose the ability to learn features? The result is actually quite surprising. What I'm showing you here is the test set negative log likelihood of several regression benchmark data sets as a function of the width of this bottleneck layer. So lower is better. And what we see is that a width of 1 or 2 in this bottleneck layer is optimal, after which performance steadily decreases. So width in these bottleneck models is strictly harmful because all that it's doing is it's decreasing our ability to learn features. And this really goes against our intuition for the role of width in neural networks. Now,
Is that true for autoencoders?
it should be, yeah.
Is this because you're missing some kind of regularization? Because if you have bits and each one of them is a feature, and then you have those weights that have to combine the feature into your final layer. That if you're not regularizing that layer, then you're probably getting similar kinds of overfitting we have seen in our, like, in your standard SVM kind of or regression kind of.
Interestingly, I think it actually might be the opposite, where I think it actually might be due to regularization. So this is kind of taking a Bayesian interpretation of neural networks, which would correspond to, say, neural networks with L2 regularization. And as you decrease that amount of L2 regularization, there's been some research that's shown that, width can actually be beneficial. Of course, L2 regularization can also be beneficial. So, it might be the case that you want to have some amount of regularization in order to make these models actually practical. But from what I can tell in my research is actually the regularization itself might be creating this limiting case. Yeah.
Or small width itself is serving as a regularization, right?
With the small width, it's complicated in the sense that you can view it as a regularization because like your model is essentially less complicated, but also something I'm not going to touch on this talk, but depth has the opposite role, where depth is actually making more amenable to learning features, even though that's also making the model more complex. So it's really, I think that like trying to map this onto like traditional notions of regularization is like, it only brings us so far with our intuition. It's actually like pretty strange. So this again is for these bottleneck neural networks here. And what you might be thinking is, what we care about is going to be standard neural networks. Importantly, standard neural networks also happen to be a subclass of these deep Gaussian process models, which is, again, this class of models that we made this reduction to help us formalize this notion of feature learning and losing that ability as we increase width. Of course, standard neural networks are going to be a degenerate subclass of these models. And again, I won't go into too much details about what this reduction means particularly, but importantly, what it means is that the findings that we had about bottleneck neural networks are also going to apply to standard neural networks, but with a few caveats. For bottleneck neural networks, what we saw is that width is strictly harmful to their performance because all that it's doing is it's causing the ability to learn features. Now, for standard neural networks, we obviously need some amount of width because we start off with a finite set of features. And so we need enough features in order to be able to model complex functions that in order to describe our data. But after a certain amount of width, once we have enough hidden units to describe functions that we're trying to model, this rather detrimental effect of losing the ability to learn features starts to kick in. And so this is what we see in practice. Additional width is only good to a certain extent, after which it starts to become harmful. Again, I'm showing the test at negative log likelihood, so lower is better. Now as a function of the width of standard neural networks. 2 regression benchmark data sets over on the left, and the CFAR10 image classification data set on the right. And surprisingly, for these small regression benchmark data sets, a width of 8 to 16 hidden units is about optimal, after which performance starts degrading. And that's really not that wide. These are very simple regression benchmark data sets, but it points to the fact that we might have been using models that have been too wide in practice and hurting performance without knowing it. For the CFAR10 image classification data set, this is a much bigger data set. It's more complex data. So we probably need about 500 hidden units before we get to this sweet spot, this sufficient capacity to model functions, which is what we see over on the right. But again, after about 500 hidden units, width starts to degrade performance. And so the big takeaway here is that wider models aren't always better. And in fact, at a certain point, they can start to become worse. And so that concludes the second part of this talk here, where again, I'll pause for some questions. And just to briefly summarize, we've analyzed the effect of width in neural networks. And again, utilizing Bayesian non-parametric theory, which we get from Gaussian processes, we demonstrate a surprising and counterintuitive result that helps to make neural networks a little bit less black box. So I can pause here again for some more questions if there are any.
So a few slides back when you had that comparison between bottleneck and standard.
Yeah.
The reason why it says infinite learned features in red is that the non-bottleneck layers are infinitely wide. Okay.
Right. And so I guess to formalize that a little bit more.
That's why you don't have plots from that.
Yeah, or that was these plots here, where the bottleneck, which we can model through like
very large.
The reason I claim that it's infinitely many features here is because these bottleneck neural networks are also guaranteed to be universal approximators. Which you need an infinite number of features if you want to have, a function class that can model functions to arbitrary precision. And if there are any more questions now, happy to revisit this later on in the talk, but I want to briefly now talk about what I aim to do in the future. And so what I've hopefully convinced you of, at least in part from these two stories, is that it's possible to improve the reasoning capabilities of neural networks and our understanding of neural networks, while also possible to improve the power and scalability of probabilistic models like Gaussian processes. And now looking forward, I aim to continue pushing this Pareto frontier to bring us closer to this important regime of high power and high reasoning. And getting there is going to require work on all of these different dimensions that I've described up here. But for now, I'd like to highlight two directions that I think offer some of the greatest promise to getting high power models that are also capable of reasoning about downstream decisions. So I just spent a lot of time discussing work on better understanding neural network architectures and trying to make them less black box. I now want to take this line of work and push it beyond just understanding our current set of neural networks, but to use this understanding to develop our next generation of neural networks that are going to better be able to encode inductive biases and quantify uncertainty. And so let me dive into that. And first, I want to talk about inductive biases, what I mean by that, and what it means to encode inductive biases in neural networks. So let's say that we have this particular data set of carbon dioxide levels in the atmosphere. And now, how do we ensure that if we're using a machine learning model to extrapolate in the future, that the extrapolations that we make with this model are going to be consistent with our prior beliefs about what we would expect to see? And we do so by specifying an appropriate inductive bias into the model. One that's we're going to use a model that codifies this general increasing behavior that we expect to see, as well as the periodic trends that we expect due to seasonal fluctuations. Now, we know how to encode and specify inductive biases pretty well in probabilistic models, but we don't really know how to do this for more complicated models like neural networks. And to explore this in a little bit more detail, here are some things that we can do with probabilistic models. We can choose inductive biases that encode domain-specific knowledge about our type of problem. And in Gaussian processes, this is usually accomplished through our choice of prior covariance function. We can choose inductive biases with desirable functional properties, saying that, for example, our model should fail gracefully in the presence of unseen data by reverting to a safe mean prediction. And finally, to choose models that are going to be well suited to our observed data, we have the ability to combine model selection with modern gradient-based optimization techniques to find appropriate hyperparameters that describe our model. And this can be accomplished through something like type 2 maximum likelihood estimation. So this is what we can do with probabilistic models, and this is going to allow us to encode domain-specific knowledge and also desirable functional properties. How do we think about doing this now for larger models like neural networks? So we have some tools for encoding domain-specific knowledge. For example, there's lots of work on structured layers like convolutional layers for computer vision, which is going to be a layer that's going to be very well suited to the types of prior knowledge that we have about natural images. And I think we're just beginning to scratch the surface at how to choose domain-specific layers for neural networks. But what I'm really excited about right now are some of these last two properties here. So being able to encode desirable functional properties in neural networks, and also being able to perform gradient-based model selection. So one of the interesting threads that comes out of my earlier work is developing priors and regularization and model architectures and training procedures for neural networks that are specifically going to encode desirable functional properties rather than relying on vague parametric regularization penalties. And so, for example, expanding this line of work will allow us to encode properties like saying that neural networks should fail gracefully in the presence of unseen data, or should avoid spurious correlations or confounding factors. And another thread falling out of my work on understanding neural networks is going beyond cross-validation when it comes to selecting model components that impact the inductive bias. And this includes things like our choice of activation function in neural networks or a choice of parameter initializations. Now, cross-validation is a wonderful tool, but it's going to be inherently limited to grid search or black box optimization techniques, meaning that we're not going to be able to search over a wide space of possible activation functions or architecture designs. And my work points towards rethinking neural network model selection and replacing cross-validation with an approach that's inspired from empirical Bayes methods from statistics, which is going to allow us to choose components against randomly initialized neural networks in a way that's amenable to gradient-based optimization, meaning that we can choose the appropriate activation function, for example, in our neural network through gradient descent. Now, this is a very high-level overview of 3 very different threads. I realize it was a very brief introduction to all of these. I'm happy to discuss them more offline. But taking a step back here, again, the goal is to develop more meaningful inductive biases in neural networks so that we can really codify how they should behave in the presence of unseen data. Now, to finish off, I want to briefly move back to uncertainty quantification of neural networks. And if you recall, I started off the talk describing some of my work on calibrating neural network uncertainty estimates using these post-processing based approaches. And this goes a long way towards getting meaningful uncertainty estimates out of neural networks. But also these post-processing approaches are going to be inherently limited. And in particular, one of the biggest limitations of post-processing calibration is that it's only going to really cause the model to remain calibrated when the model is exposed to data that is similar to what it was trained on, so-called in-distribution data. It's going to really fail to remain calibrated or have some meaningful notion of uncertainty when it's exposed to data that differs sufficiently from data that it saw during training, when it sees so-called out-of-distribution data. I'll go into a little bit more detail about what I mean by this. But before I do, I want to emphasize this isn't just a limitation of this post-processing approach. Out-of-distribution uncertainty estimation is a really hard problem, especially with neural networks. And to demonstrate this, let's consider an alternative method to getting uncertainty estimates out of neural networks, which is using an ensemble of multiple diverse neural networks. There's many recent papers that have claimed that this is the gold standard for uncertainty quantification with deep learning. It's also going to be a lot more expensive than this post-processing approach because we're relying on multiple networks now rather than a single neural network. But here's the intuition that's offered by many recent papers for why this should be the gold standard for uncertainty quantification. If we feed data into these models that is, again, in distribution, so similar to what we encountered during training, it's likely that each of these networks is going to make a similar prediction. If we instead feed something nonsensical into this neural network or something that is very dissimilar to what we encountered during training, again, what we're calling out of distribution data, now there's nothing constraining these networks to produce a similar prediction. And in fact, the inherent diversity of these networks should cause them to make diverse predictions. So this is what the current consensus tells us, is when we have variance amongst the predictions made by our neural networks, this should be indicative of when we have out of distribution data. But in some of my recent work that's currently under submission, there's a startling finding that breaks this intuition. What I'm showing here is the expected ensemble variance for in-distribution data, the blue line, and out-of-distribution data, which is the orange line, after we condition on the uncertainty expressed by each of the component models of this ensemble in isolation. And what's really surprising is that with this conditional expectation that I'm plotting here, after we control for the uncertainty of the individual models in isolation, there's no difference in the amount of variance that this ensemble expresses for in-distribution and out-of-distribution data. And this is really surprising because it really breaks our intuition about ensembles. What this is saying is that variance amongst ensemble members is not at all indicative of when our data is out of distribution or not. And again, this is supposed to be the gold standard for neural network uncertainty quantification. So here's where we're at. This post-processing approach, which I started off at the beginning of the talk with, doesn't really work for out of distribution data. But this expensive gold standard alternative also doesn't really work for out of distribution data. This is a really hard problem, and it's a great opportunity to draw inspiration from probabilistic models like Gaussian processes, which are actually really good at expressing high uncertainty when exposed to data that is dissimilar to what they were trained on. We can think about designing new uncertainty propagation layers for neural networks that could rely on some of the same analytic computations for Gaussian process uncertainty estimates. We could think about hybrid models that combine neural networks and probabilistic components, such as the deep Gaussian process that I described earlier. And finally, we could develop meaningful diversity regularizations for ensembles so that we can get actually good variance estimates from them, building on top of the work that I just discussed. So uncertainty quantification and encoding inductive biases in neural networks are just two of the areas that I'm really interested in pursuing in the future. I also am interested in a number of different directions as well. Some focused on improving probabilistic models, some focused on improving neural networks. And I'd love to chat more about any of these areas one-on-one. I realize this was a very quick overview of a lot of future work directions. But progress in any of these areas is going to be essential to allowing us to use machine learning models in these high-stakes settings that we care about. And finally, if there's anything that I hope you take away from this talk, is that all of these directions really require that we continue to study both neural networks and probabilistic models together and think about the intersection of the two of them, because this is how we continue to push this Pareto frontier here. And with that, I would like to thank a whole host of collaborators who helped to make this work possible. And I have time for, well, I don't know, I'm almost out of time, but I'll stick around for more questions.
So since the Zoomers might run away, let's first see if there's any people on Zoom with questions. Okay, there's people clapping and there's a hand raised. Ali Reza?
Yes, very interesting talk, excellent presentation and work. I just wanted to follow up on the discussion you had regarding the width in the bottleneck type architectures.
Yeah.
How much of that discussion is dependent on your sample size for the training? And I was wondering, in fact, like you had one of the slides when you had a big data set, basically you showed that, you know, if you increase the width, your error goes down, and then it start, you know, increasing, and that probably is, you know, where exactly it goes back up would be sample size dependent. I was wondering if you've looked at, you know, same maybe simulation, but with larger sample size, and see if actually it shifts to the right in terms of when you start, you know, increasing your error.
Yeah, that's a very good question. And I think your intuition is exactly correct, if I remember the experiments correctly. So it is the case that sort of this, one thing that isn't quite demonstrated from the plots that I show is that the error of these models in the limit of infinite width actually like asymptotes out. It's not that it just, you know, explodes up to infinity. And so both this asymptote depends on the amount of data that we have. So you're going to end up with a, you know, asymptotically less error when you have more data, but also exactly like what you were saying, this in the case of standard neural networks, that sweet spot where we get, you know, the best performing model with more data, we're going to require more width before we hit that sweet spot.
And does it apply also to these bottleneck type architectures that you showed, you know, basically you start increasing your error as soon as you go to larger widths than one?
Right. Sorry. In the bottleneck neural networks, it's still very much the case that,
okay,
like smaller is always better, but like you're going to end, the asymptote that you end up with is going to be lower when you have more data.
Okay. One other question, very quick. You know, what are your thoughts in terms of you know, things like Bayesian version of neural networks when it comes to uncertainty quantification associated with, you know, deep learning?
Yeah, that's a very good question, and I would be able to probably rant for hours about that. But maybe the high level, my high level thoughts on that is, I think a major challenge is one, ensuring that the types of approximate inference that we're using for Bayesian neural networks isn't creating other confounding effects that we would care about. And so I think that's for example, I know that there's been a lot of interpretation of ensembles as approximate Bayesian inference, and what the sort of recent study that we looked into is showing is that it's not necessarily giving us reliable uncertainty estimates, which perhaps is to some extent, you know, a product of doing poor approximate inference in that case. But of course, one big thing with any sort of Bayesian modeling is things are very dependent on the prior. And so it's not even clear that, you know, this choice of having what is, you know, typically the case, like Gaussian prior on our weights, you know, corresponding to L2 regularization, it's not necessarily clear that that's the appropriate prior that we would even want. And so I think that, you know, a Bayesian approach to neural networks could be a really cool way to do uncertainty quantification. But I think that there's a lot of work before we would get to a point where that would be, you know, practical, but also have guarantees that we would want in practice.
Awesome.
Cool. I
Thank you
think
very
we'll
much.
take one question in the room and then the rest of the questions offline. Are there questions in the room, Sriram?
Yeah, so there's been a lot of recent work on combining, for example, symbolic, like programmatic models with neural networks.
Yeah.
Everyone's running around saying neurosymbolic, differential programming or probabilistic programming, right?
Yeah.
So what do you think that's a way to combine both your deep reasoning and your scalability?
I think it's a super cool area. One thing that I didn't really have time to get into here is I think we can sort of think about one advantage, I think, of neural networks or hierarchical models in general is one interpretation that kind of comes out from some of this research that I've had with this probabilistic interpretation of neural networks is that they're a way of encoding soft constraints into the data. So for example, with these deep Gaussian process models, you could compose them of stationary Gaussian processes where that's like that basically means that I'm assuming a priori that my data is shift independent. But when I combine them in a hierarchical fashion, I end up with something that's non-stationary. It's going to mostly be stationary, but when the data basically indicates that it shouldn't be stationary, it's likely to induce a bit of non-stationarity, which one way of interpreting that is that this hierarchical modeling that we get from neural networks is helping us to encode like soft or local versions of constraints that we would otherwise get through, shallower versions of models. And so one thing, again, this is maybe, a very short answer to that is I think that there is a lot of interesting work when it comes to combining, like neurosymbolic, but I think you're going to end up with something that is going to be fundamentally different because the symbolic nature is probably going to be encoding very hard constraints, whereas perhaps some of these like probabilistic models and hierarchical models are imposing softer constraints.
Let's thank the speaker again, and he'll stick around in the room for questions.